Hey guys, welcome to our today's tutorial. We are going to look at the question that came in 2016. Let's try to look at this. This is under electromagnetic radiation, which is spectroscopy. Yeah, so the question is the UV spectrum of this compound is determined in 95% ethanol. So 220 millimeters or nanometers, sorry, then log 4.0, and that. Okay, the IR spectrum is obtained on a neat liquid sample. So here what we need was, we are required to work out the molecular structure. That was the question. I'm sure I didn't just include. So we are required to work out the molecular structure of this compound that was placed in these components. So we have mass spectrum, infrared spectrum, as well as NMR spectrum. So let's try to look at this. We need to start with infrared spectrum, then we come to NMR, then the one that will confirm the molecular weight is mass spectroscopy, which is mass spectrum. All right, so let's start with NMR or infrared spectrum. Infrared spectrum, as we know that it is only applied or is used to determine or to identify the functional group that are present in that drug molecule. So now here, from 1500 going this side, we use to identify the functional group. Even here on the fingerprint, there is one mostly that is used to determine. Mostly we find ether there. All right, so let's try to look at this. So here they are saying from 3200, which is 3200 to 2800, there is a sharp peak here. You can see this sharp peak here. You need to know these are the common functional group, which is in between or near 3000 per centimeter or frequency. That is a CH stretch. So here it is common, and mostly it is found on each of the compound. So here I'm going to write. Okay, so this is I spectrum or IR spectrum, which is infrared spectrum. I'm going to write like near. So here, okay, so I'm going to write near 3000 per centimeter is CH stretch. Okay, so like that. Then I'll come to the hour, which is this one, which is between 1800 to 1600. So again, this one you should know it, please. It is a common functional group which is in between or near 1720 or 1700. That is a carbonyl. That is a carbonyl group. So don't forget about those. Those are the ones that are common functional group. Between 3200, which is near 3000, that is CH stretch. Then between 1600 and 1800, in between, for example, 1720, 1730, 1700, which is 1700, that is carbonyl. So I'm going to write here, which is near 1700 per centimeter. That is a carbonyl group. So don't forget about that. Then we'll come to this. The other one here, from here going this, we can only have one functional group, mostly the one that is most the one which is sharp, like, yeah, for example, look at this one, which is from 1400 to 1200. This peak here, which is formed there, that peak is the one that is called an ether. Okay, we'll check, which is near 13,000. So here I'll just try to write like this, near 13,000. So here it can be between which is 1300 to 1000, or like this. I'll just say near that, which is an ether. But let me try to check on the mass or on the infrared spectrum, the one that I have. These are the common ones. Don't forget about that. That's why I didn't even have time to go and check there. So let's go and check on this one. So this is an infrared spectroscopy manual that I'm having. Let me try to check. I'll be checking, which is near 1300, which is 1300. All right, so as I said, that is an ether, so let me just go on ether. All right. Okay, so where am I? Okay, where am I? All right, so you can see this one here, which is an ether, which is CO stretch, and this is 1300 to 1000 per centimeter, which is in between 7.7 to 8 to 10. This one, take note to that one. Let's go check there, but it's between 1300 and that is CO stretch. So when you look at this diagram, you find that this one, it is in between. So this is 7. I'm sure you can't see, but here this is 7 and this is 8. So it is between 7.7 somewhere there to somewhere 8 point something. So this is an ether, you see, and it is on this line. You can check. This is between 14, which is 1200 to 1200. That is 13, which is 1300. So this one is an ether, which is CO stretch. So I'm going to write there, which is CO stretch, like that. So that is my data on I spectrum, which is IR spectrum, or the infrared spectrum. So let me come to NMR, the one that will give us the detailed information about the structure of the drug molecule, or the environment in which this drug molecule or the atoms are found in the molecule. All right, so let's try to go on the NMR. So when you look at this NMR spectrum that we have, look at this one here. This is a triplet. When you look at triplet, remember we said triplet, and here you see the number of hydrogen. So here, how many number of hydrogen? There are 3 number of hydrogen. And triplet, it means that it is connected to the one that has how many number of hydrogen? 2 number of hydrogen. Remember when we are having n+1 rule to give us the triplet, which means the number of hydrogen, triplet it means is 3. The number of hydrogen on the adjacent atom is 2 to give us 3 here. So we'll say it is connected to CH3 because of the triplet. So we'll say this one, we can check even the number here. These small numbers which are here, which is 1, 2 up to 10, these are chemical shift, which are expressed in ppm. So here it is in between 1.2 somewhere. So I can go and write there on my NMR. I can go write something like triplet here, which is okay, so here it is 1.2, the chemical shift. Then how many number of hydrogen? It was 3, like this one. Connected to what? So these are the things that we need to write here. So connected to CH2. So here connected to CH2. Right, so we go to the next one here. So see this one, this is the quartet, and remember quartet here, it has got 2H like that, and it is connected to the one that has how many number of hydrogen? 3 number of hydrogen, because we use n+1. When we say n+1 is equal to 4, then number of hydrogen on the adjacent atom is 3. So this one is connected to the number of hydrogen which are 3 on that atom. So what am I going to do? I'm just going to write here to say this is a quartet. So this is a quartet. Let me see the numbers. See this one, it is in between 4.4 to 5. So here it can be 4.3 somewhere there. So these are just approximate numbers. So here it can be 4. Okay, so 4.3 like that one, then which is 2H connected to, so CH connected to Right, so I've said it is connected to CH3, but remember the hydrogen here, it has got already, or this carbon has got already how many number of hydrogen? 2, like here the way it is. Then you say it is connected to CH what? 3, like that one. So what of this bond? Because for it to be stable, and the carbon atom has to have how many number of bonds? 4 bonds. It has connected to 2 hydrogen and this methyl, which is CH3. Then what of this bond? So we say and it is connected to the other one. So where is it connected? Where is it connected? So here I'm going to say and. So remember, when you are looking at the chemical shift on the first video, we said from 4 to 4.5, it means that CH2 is connected to O. From 4 to 4.5. So this one is connected because of 4.5 is on the downfield. It is more closer to the one that is more electronegative atom compared to these which are on the upfield. Compared to these which are on the upfield here. So I'm going to say here it is going to be connected to CH3 and also the oxygen there. Right, so I'm going to the next, which is this. All right, so have you seen this? This is a mount plate. So this is a mount plate. So mount plate, you should know that when you have a mount plate, it means you have a ring or or aromatic hydrogen there, aromatic ring. So this one, it tells you that you have aromatic ring. So which is it has got how many number of hydrogen? 2 number of hydrogen. That is aromatic ring. So I'm going just to write. So here I can even tell to say even on the NMR or on the infrared spectrum here, this CH stretch which I have here, which I've found that CH stretch is my functional group there, it is aromatic ring, or it is aromatic hydrogen. So here I can come and write there, this is aromatic hydrogen there. You see? So CH, which I found here, it is aromatic hydrogen. So let me just say CH here, which is aromatic hydrogen, like that. You see? Then here we say I'm going to write mount plate, which is here when I check, it will be in between 7 to 8, so it can be 7.7 somewhere or 7.5. So I'm going to write here which is 7.5, like that. Then which is what is this? A benzene. So this is a benzene ring, which is connected to what? So it is connected to the functional group, which is here, which is C, which is the carbonyl group, like you see. So having this data, we can able to write or to draw the structure of the molecule, of this drug molecule, which we want to analyze right now. But let's try to go on that, on the mass spectroscopy. So here I'm going to write mass spectroscopy, which is mass spectrum. Mass spectrum. Let's try to analyze the mass spectrum. Yeah, so this is the mass spectroscopy, or the mass spectrum that we are having, this one. So when you check, this is the mass, this is the mass that we have. That is the mass of the drug molecule that we want to analyze, or the sample that we want to analyze here. So now let me write so here the mass of the substance, the total mass of this substance that we have is 222, like that, you see. So when we come up with the structure according to the data that we have gathered in the IR spectrum and also NMR spectrum together with the mass spectrum, we are going to tell that, or we are going to find the amount of or the mass of that substance, then it needs to correspond to this which we have there, you see. So now let's try to look at that. Let's try to find the fragment lost, then and connect and find the structure. So I'm going to write fragment lost. So there what I'm going to do is, this is the mass, which is 222. I'm going to say 222 minus 177. So when I say 222 minus 177, I'm going to have 45. So when I say I'm having 45 right now, I'm going to the mass spectroscopy manual that I'm having, then I check and correspond to the things that I have, to the data that I have gathered. So let me go to the mass spectrum, or the mass spectroscopy manual. So this is my mass spectroscopy, which is the manual of common fragment lost. So these are the common fragment lost. So I'm going to the 45, the one that I found when I said 222 minus 177, it has given me 45. So here, where is 45? Okay, so this is 45. So I'm going to check 45, 45, 45. Okay, so this is my 45. When I check nicely, I'm going to find something like this, you see, which is CH3, CH2, and O there. So I'm going to get this, which I'm having, and write. So when I say 222 minus 177, my answer is going to give me 45. Okay, so 45, I've said on the mass spectroscopy, I found this, which is CH3, CH2, then O like this, you see. So that is the one that I found. That is the fragment lost number 1. So I can even say, or I can even extend it to see where this is going to be connected. So what am I going to do? I can do 222, or I can do 177 minus 149, or 222 minus okay, let me just say 177 minus 149. 177 minus 149. So let me do that. So 177 minus 149. What am I going to have? 177 minus 149. 177 minus 149. I'm going to have 28. Alright, so I'm going to have 28. So let me try to go on the mass spectroscopy, the one that I'm having, so that I check. So 28 there, here this is 28. Okay, so I'm going to check nicely. See, I found this one, which is CO there. And on my data, on the infrared spectrum, I found that there is C, which is carbonyl. So this is CO, which is connected to that. So I'm going to write there now. So I can do fragment lost, which is 177 minus 149. What am I going to have is 28, which I found that is CO. You see, so this CO is the one that is connected to this. So if you want, you can say O fragment lost, which is starting from 222, the total minus 149. What am I going to have? So when you do 222 minus 149, you're going to have 77, or 73, sorry, 73. So when you check 73, let me go and check on the mass spectroscopy. So 73 there. Okay, on 73. So here this is 73. You see this one. So here CH3, CH2O, then connected to the one which is the carbonyl there. So I can write even this one. I can write. So I'm going to write. So I'm going to write like, okay, let me write here. So it will be CH3, CH2, then O, then connected to this one with this like that, you see. So this is what we are having right now. Then when you check there, which is our for 149, which is let me just go there, this here, which is 149, you can check on the mass spectroscopy. So here you find that there is no 149 there, so that one is uncharged one. All right, so now let me try to draw the structure. Okay, so look at the data that we have gathered, which is on the IR spectrum, on the NMR together with this, which is mass spectrum. So let me go here. Okay, IR spectrum, I've gathered this information, which is CH, which is aromatic, carbonyl, and CO stretch. Then here, this, remember we said this, which is CH3 connected, or HH3, which is CH3 connected to CH2. Then here we are saying 2H, which is CH2 connected to CH3, which is the same here, CH3 connected to CH2. Here they are saying CH2 connected to CH3 and O. And check here, you are going to find that CH3 is connected to CH2 and O, which is this data which you're having here. CH2 is connected to CH3 and O. That is that. So here CH2, when you check here, this CH2 which is connected to CH3 and this oxygen there. Then when we come here, we're going to find that here they're saying benzene here, which is multiplate. Benzene ring is connected to a carbonyl there. You see, so from this we can write a structure. But on the fragment lost, we have found this, which is the one that we have found here. So here I can write the structure to say I found on the NMR, I found that CH3 is connected to CH2. This CH2 is connected to CH3 and O. You see? Again. Then on the mass spectroscopy, you see, this is the one which is here. On the NMR, this is the one. So this, we're going to say, okay, let me just write it so like this. So here it will be CH3, CH2, which is O here, then here C, like that one. Then we said benzene is connected to, so this benzene is connected to the carbonyl. Let me just write it well, carbonyl, let me write it well. Okay, this is the carbonyl. So when you count the mass of this, let's try to count the mass. Let's try to count the mass. So when you count the mass, you're going to find that the number of carbons are just here, they are 6, 7, 8, 9. So they are 9. So 9 times 12, you find you have 108. So you're going to have 108 here, 108 like that. Then plus how many oxygen do we have? 2. Plus which is 32. Plus 32, you're going to have 140. When you add this one plus 32 is 140. Plus how many number of hydrogen? 1, 2, 3, 4, 5. Then 6, 7, 8, 9, 10. We're going to have so the total you're going to have 150 when you add this one and 10 there. So that is 150. But when you check there, you're going to find that our mass, the total mass which we have written is this one. So the total mass is this one, which is 222 there. So it means that this is unbalanced. It's not balancing. Okay, let me go and check on okay, let me go and check here. Okay, this is our NMR. So see here they are saying here you have 3 number of hydrogen. Here you have 2 number of hydrogen. Then on the benzene here you have 2 number of hydrogen. So the ratio is 3 to 2 to 2 like that one, which is 3 to 2 like that. You get 3 to 2 to 2. So this is the ratio that we are having here of the number of hydrogen of this compound. So look at that. We see the benzene, which is the multiplate, has got 2 number of hydrogen. Now let's try to look at the compound that we are having now. So this one is not balanced, so I'm just going to have this. So here I'm going to say our structure is not unbalanced. So the ratio is 3 to 2 to 2 like that, you see. So here they're saying here you have the number of hydrogen 3, here you have the number of hydrogen 2, here on the benzene you're supposed to have the number of hydrogen which are 2 again. But here we have how many number of hydrogen? 1, 2, 3, 4, 5. So we have 5 number of hydrogen there. So what am I going to do for me to have the stable structure? Because here the mass is 150, but what I want is 222. So what am I going to do? I'm going to say let me just multiply this with the least even number for me to balance this this ratio. So I'm going to multiply with the least even number, which is 2. So 2 times 3 is 6. 2 times 2 is 4. 2 times 2 is 4, like that, you see. So here it tells me now to say I'm supposed to have the number of hydrogen here on the CH3 6. Then here I'm supposed to have the number of hydrogen 4. Then on the benzene here I'm supposed to have the number of hydrogen how many? 4 as well. So what am I going to do? So this I've multiplied with 2. Even this structure I'm going to duplicate it with I'm going to have 2 here. So what am I going to do? I'm going just to connect here the same structure which is connected this side, you see. So let me just remove. So I'm just going to connect it here. Okay, so like this one. Okay, like this here. So there's no space, it was supposed to be going straight. Then here, or like that, you see. Then here it will be CH3 CH or CH2 CH3, like that. Another way I can, yeah, just that. So here you can able to tell that here there are how many number of hydrogen on the CH3? This CH on the CH on the C there, the first one, number of hydrogen there are 3 plus this there are 6, which is this one, you see. Here there are 2 plus this 2 there are 4, which is this one. Now check on the number of hydrogen on the benzene here. You find that the number of hydrogen here we just have 1, 2, 3, 4, and here you have 4. So this one is balanced. So this is the structure that we wanted to come up with. So let's try to find the number of the mass so that we can see if it corresponds to the one that we have been given in the question. So I'm going just to count the number of hydrogen, the number of carbon. Here we have 6, 7, 8, 9, 10, 11, 12. So I'm going to say, so let me just lab this. I'm going to say, okay, I'm going to say 12 times 12, which I'm going to have 144, like that. Then here I can say number of oxygen, I'm having 4, so it will be 4 times 16, which I'm going to have 64. Then here the number of hydrogen, when I count here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So I'm going to say 1 times, so here it will be 14 times 1, which is 14, like that. Let me try to find the total now. 144 plus 64 plus 14. So the total that I'm going to have is 222. So that is the mass that I am having right now. So let me go and check if the mass that I'm having is 222. So here, this is the mass that we have been given. Even on the question, when you check, that is 222 there. So this can prove that you have answered this question correct. So this is what they wanted us to write or to describe the structure, to work out the molecular structure of this drug molecule. Yeah, so you know most spectroscopy is used in the drug analysis in pharmacy. So guys, thank you so much for watching this video. Please subscribe. Don't forget.